Well, good evening and welcome to TELUS, my favorite science museum. And I'm so glad you've come this evening on a rainy, dreary evening with the observatory closed again because of clouds. We always blame marketing when it's cloudy, by the way. So, if you're sending in those cards and letters, it's their fault. I'm Dave Dundee. I'm the Director of Education. I'm so glad you're here. And we've got a great night for you, great talk. And just want to let you know about some exciting things coming up. We always have exciting things coming up at the museum, but just in case you're not aware, we've got a new exhibit opening at the end of the month on the 30th, all about patents and patents of new scientific equipment and old scientific equipment. And there's even a computer quiz if you can guess from the drawings what the patent's for. I successfully got 1 out of 8 right. But anyway, moving right along. We will have a special program on April the 8th. The partial eclipse of the sun is happening here. It'll be about 84% of the sun covered. We'll have our observatory here, and we'll have live streaming of the total eclipse right here in this theater, and coming out of places like Texas, where I will be, and some other sites as well. So no matter what the weather is, we will find a clear site to broadcast the total eclipse, unless it's cloudy over the entire eclipse path, which I don't think it will be, but anyway. We have, for those of you who have friends or family, or know of friends or family who would like to come to our sensory-friendly mornings. That's on April 27 and 28, and we open the museum a little bit early, and it's quiet. We have a lot of the noisy machines and things turned off, and it's a little bit less traffic if you need to be in that kind of environment. Next Sci-Fi Night will be on April 26th. We'll have Tony Martin, professor from Emory here, talking about his new book called Life Sculpted, all about early fossils and dinosaurs, and it'll be full of adventures and so on. And then over spring break, yes, spring break is a big week for us here at the museum. We usually see about 11,000 guests in that 1 week alone, and it's going to be a wild week. We're going to have activities every day on science, family activities, and just take a look at our website. We've got all sorts of cool stuff coming up. Lunch and Learn, our next Lunch and Learn on April 24th, we'll be talking about service dogs, teaching old jobs and new tricks to service dogs. So that'll be kind of fun. And speaking of cool astronomy things going on, our planetarium is closing in April, and so we'll be closing on the 22nd and reopening on May the 18th with a brand new planetarium projection system. It's going to be awesome, ladies and gentlemen. It's going to be a laser projection system, and don't think about lasers as just little bright lines and stuff. It'll be gorgeous, what you're going to see, but it will more than double the resolution of our current system, and so the night sky will be awesome, and so will all the other projections in the planetarium. So look out for announcements for that. We'll have special celebrations with the opening of that machine. So tonight I have the honor of introducing Danielle Crocker, and she is a senior test manager on Boeing's Starliner program. The good Boeing, the one that's building rockets, not the other one we've been hearing about on the news. And you have nothing to do with doors, do you? No, okay, good. All right, we're good. And she has been involved with testing and certifying multiple frames of commercial aircraft, the Artemis core stage. That's the Artemis rocket standing right there. We'll be hearing about tonight. And now she's working on the Starliner program. And we're so excited to have you here today, Danielle. So welcome to TELUS, and we're excited to hear your talk.
All right, thank you.
Big
Hi, guys. All right, so I'm going to give you a fair warning. I like to move around a lot, so I'll probably be walking a lot. And questions are always welcome, even in the middle of things, okay? So we'll just start there. So certifying spacecraft. Okay, well, we all see spacecraft. We all think it's awesome. We all think it's interesting. But how do we actually get to space? So we actually have 4 different types of testing that we have to do on any space vehicle before we can actually get up to space. The first one is developmental testing. So developmental testing, think of it as an engineer's dream. They have an idea, and they want to figure out, does my idea work? It's when we get to play with all of our Tinker toys and try to make things work, and we get to go, oh, does this work? Oh, no, that didn't work. Okay, let's go back and try it again. So we do a lot of that with developmental testing. Qualification testing. Qualification is done on individual components, and it's going to look at a wide variety of things. And in all honesty, the qualification testing has some of the coolest videos. So I'll get into some of that here in a little bit. Because the cool thing about qualification is you get to make things break. And if you ever like to make things break, that's where you want to be. Then you get into the certification testing. Now, certification testing is more of an integrated type thing. You're going to look at how the entire system works together. And all of those parts that they qualified, when you actually put part A with part B, do they connect well? Do they work well? Do they talk to each other? And then you get into acceptance testing. Now, acceptance testing, some of that actually happens while you're doing your certification tests. And your acceptance testing happens to be a subset of your certification tests. Now, the one thing that is very different between acceptance testing and all of the others is acceptance testing is done during every single build of every aircraft that goes into space, whereas the rest of it happens well before. So let's get into it. So again, developmental tests, right? This is where we get to think and try, and we get a lot of iteration. So this is where you get the people sitting down and they're going, wow, I have this idea, I wonder if it'll work. And so they go and they procure little pieces and parts, and oftentimes when we're doing developmental testing, this is where we're going into whatever we find at our house to build, right? Do we have popsicle sticks, balsa wood? What kind of chemicals can I mix up? This is where we really get into that kitchen engineering, that kitchen science that you get to do as a kid, right? Do you guys remember like doing those really cool projects in school where they say, can you build me a bridge? Here's a bunch of popsicle sticks and tape. Now build me a bridge that's gonna hold 10 pounds, right? We all got to do that as a kid, and there's a lot of creativity that goes into that. And the most creative engineers really take part in this developmental testing, because you have to be. This is where all the creativity comes out. The artistry of engineering really exists in these developmental tests. And it's really iterative. So you try something, some parts of it work, some parts of it doesn't, and then you go, okay, what did I learn from that? What can I change to make it better? So if you're trying to build an airplane and you want it to fly 10 feet, paper airplanes, right? We've all made them. Say you want a paper airplane, you say, I want it to fly straight for 10 feet. Well, okay, the first time you build your airplane, it only goes 5 feet. How do you fix it? What do you do next? What do you try? That all happens during the developmental stages of testing. Again, it's really early on. Before we even really get anything real, it all has to be developed somewhere. Whoops, too far. Qualitative testing. Now, guys, I'm going to bounce back and forth from this slide to a couple of videos. So qualitative testing is where we really find out how individual components work and to make sure that they actually meet all of the requirements that we need to go into space. You guys see this laundry list of things up here? We have to test a lot of stuff. You know, when we go into space, we're going into a different environment. We have microgravity environments that we have to deal with, right? Okay, so are we going to be able to survive microgravity? But you know, in order to get into space, we have to be able to survive multiple G-forces, up to 9 or 10 G-forces, as we try to exit Earth's gravity. So we have to be able to go through and do that as well. So we end up doing a lot of structural testing. Let's see, right here, and the stress load. So we have some acoustic testing. Now that acoustic testing, that's when you are actually dealing with things from like the engines, right? When you launch a rocket, how many of you guys have ever seen a rocket launch? Yeah, quite a few of us, right? You guys know that really loud brrrr that comes with the rockets? That actually, when they're on the launch pad, actually reverberates and will actually start to shake everything. You guys have seen launches. How many of you guys have felt the shake from the engine. Yeah, it's big, right? So that's what you're looking at when you do acoustic testing. Now, modal testing is really kind of interesting. Have any of you guys heard of modal testing? Yeah, I didn't think so. It's kind of one in the back. Has heard of modal testing? Modal testing is when you have these interesting dynamics going on. As a vehicle or a structure moves, it has these harmonics. And if you get into a harmonic, so you get this wave sign, this waveform going. What you want to engineer is that regardless of the frequency that you see, you want those waves to dampen out and go away. But sometimes you end up in a situation where those waves start growing on one another and they compound. How many have heard of the Galloping Gertie Bridge out in Tacoma, Washington from like the 1960s? Right, you guys have seen that video where it just is like, wait, this crazy wave? That's actually modal. That's what happens during modal testing. And if those waves keep growing and growing and growing and they don't dampen up, it falls apart. That's where you'll have structural things that fall apart. And you actually see a lot of that in your life on a normal daily basis. Part of it's, you'll get those wind harmonics coming through the bridges. Did you guys know that when military groups actually march across bridges, they alternate who steps when? And they do that specifically to avoid modal vibrations in the bridges. And so we actually, when we're going to design and engineer bridges, spacecraft, anything, we actually have to think about what kind of harmonics and what kind of vibrations they're going to see, and can we engineer it out so it actually dampens out instead of tear apart what we're trying to put together. Vibrations, similar type things, but we will actually look at temperature compatibilities. Is space hot or cold? Yes is the right answer, because if you're in the dark and you're not in the sunlight, it is very cold, right? But if you're in direct sunlight, it's very hot. So you have this huge temperature swing that you have to design for. So you can't make it to the point where if it gets so cold, it gets brittle, but you also can't have it so if it gets so hot that it melts. And so it really has to regulate. So now you have to have systems that you're going to have to heat sometimes. Because if you're in the shadow of the Earth, it's really cold. But do electronics like it when it's cold? No, not really, does it? So we got to make sure we can heat it up. But wait, do electronics like it when it's really hot? No, so we got to cool it down too. So when we do qualification testing, we're actually checking to make sure that we can keep those temperature variations low so that regardless of the environment we're in, all of our electronic components still work. We're going to look at our pneumatic systems. Who knows what the pneumatic systems are? That's kind of a crazy word, pneumatics. I got one here who knows who pneumatics are. Couple. Yeah, so the pneumatics are your hydraulic systems. It pushes air through, right? Sometimes we're pushing air throughs for pneumatics. Sometimes we'll have hydraulics instead of pneumatics where you have hydraulic fluid. But it's actually what forces the parts of the vehicle to turn and move. So I want to show you something with pneumatics. And this is going to be an interesting, fun video that includes both pneumatics and propulsion. All right? And so this is actually a mix of a certification test as well as a, let's get in here. Oops. I want this one. This is actually a mix of a certification test and a qualification test that was done on Artemis 1. So Artemis 1, this is the core stage of Artemis 1. And it is the largest, strongest rocket ever put into space. But before we got there, we had to do what we call a green run. Now, a green run is a hot fire test. So basically what we did was we strapped our rocket into a building and we acted like we're going to launch it.
Go for engine
So
start.
we actually started the engines.
Has been okay.
And by the way, I was there the day this happened.
And all
We started
personnel.
our engines,
We've got engine
and we
start.
actually ran it for the
Count
entire
official.
8.5 minutes
System. And
that the
ground.
rocket is expected to launch for the core stage before it gets jettisoned. So you see this plume here, that's the exhaust from this rocket. This rocket uses liquid hydrogen and liquid oxygen. So our exhaust is water vapor. So on the day of, it was actually quite a sunny day. From the vantage point that we had watching this, we could actually see rainbows in the clouds. That wouldn't have existed if the rocket wasn't there. So you can see the rocket starts, And they're going to actually show some gimbaling. Now, gimbaling is where the engines are actually going to move around a little bit. And that's how we're testing our pneumatics and our hydraulics, is making sure that gimbaling is actually operational. Now, this was really loud. And remember how I told you guys we learned stuff? So see this tape underneath? That tape isn't normally there. We put it there specifically for this test. Because unlike most of the times, this rocket, after doing this hot fire, was actually going to be launched for real. So we put that tape underneath to actually protect a little bit of the vehicle so that we could minimize how much refurbishment we had to do to the vehicle afterwards. So see the gimbaling? The engine's moving around? We're actually intentionally making it do that. That's not just from the vibration. Now you see that fire? That shouldn't be there. Fire's bad. Now, what was interesting is that we actually almost canceled the rest of this hot run, this green run, because of that fire. But remember how I said we were doing this as a qualification and certification test? So we had a significant amount of instrumentation on this vehicle to be able to see what the real behavior of the vehicle was. So underneath that tape, there's a layer of cork, which is a type of insulation that we use. And underneath that cork were a bunch of thermocouples, basically things that we could read temperature with. So as we're sitting there and we're going through this hot fire, what's really important is what are the temperatures that the vehicle's seeing? Because again, we don't want to get it too hot because we don't want to make it brittle for later, right? So we were watching the thermocouples. The thermocouples directly under that fire read 74 degrees Fahrenheit. And because it read 74 degrees Fahrenheit, we were able to continue with the test. Now we needed to run the test for a full 512 seconds to be able to show that this vehicle could last what it needed to last in real life when we actually go to launch it. This type of green run test is only done once in the entire life of the program. And because you actually have to do it with the real vehicle, it becomes really kind of crazy. But think about this. This is a rocket the thrust on this thing, something like 4 million pounds of thrust, and we have it strapped into a building. Let me tell you, it's a really interesting thing. Think of how strong that building has to be. So when we start talking about our Tinker Toys, not only do we have to test the vehicle, but we actually have to create the things that allow us to test the vehicle. Who thinks they could design a building to hold down a rocket? Yeah, maybe, right? Now the interesting thing about this rocket, about this building, is that this part in here is actually what we call the hardcore, and it's actually built to withstand that rocket blowing up in case it didn't work. But we actually have to think about that. So we actually evacuate out all along the area. There's nobody really in there, and even the day that we did this, we did not have anybody in that building. All of our control systems for this building was a mile away, just because we want to make sure the engineers don't have a problem. But for the full 8.5 minutes, this guy ran. But we were testing the propulsion systems, we were testing the pneumatic systems, we were even testing the avionics, making sure that we can control what is it doing. When I tell those engines to gimbal with my computers, is it actually doing it the way I want it to? And you can see, obviously, we had lots of video. Now, who wants to see something blow up? Yeah! The blowing up stuff's always fun. So when we talk about structures testing, again, this is a qualification test. So this is the liquid oxygen tank. You think it's little or you think it's big? It's actually the largest part of the rocket. So if you see this rocket here, right? I'll pick it up this way, if I can get my hands on it. Man, this sucker's stiff. All right, so this part of the rocket here that you're seeing, this huge thing, runs from right here to here. So it is probably about 2/3 of the spacecraft, 2/3 of the core stage. It's pretty big, right? But this is what we call the liquid hydrogen tank. Now, remember when I told you guys that we have to make sure things are structurally sound? And I said the fun thing about qualification testing is you get to break stuff, right? So this is actually the test that we did that was a test to failure. So we intended to break it. This isn't an accident, this is what we intended to do. Now, as you can see, we have wires running all up in here. We have strain gauges. You see a couple things popped off. We're like, okay, a couple of things popped off. Not a big deal. But these wires that you see all in here have strain gauges, so we're watching what's happening structurally to the vehicle as we're doing this. So the orange that you see is what we call TPS. It's the thermal protection system that sits outside the metal tube that is the rocket. Oh yeah, big boom, huh? Did you guys catch that? So you see how the seam is almost a straight line where it broke? That's actually a weld seam. So when this gets put together, it actually has 5 panels that get welded together all the way around to build your circle. Now, that's what actually builds the circle of that. Now, it gets welded together, and during every single build of that tank, we will do what's called a proof test. Now, when we do proof testing, this is actually part of our acceptance testing. And when we do that testing, we actually put it into a building, and the building is extra fortified, and we actually do the proof testing before we put the TPS on. And what we do is we lay it horizontally, so it's laying down on the ground in this building. Now, when I talk about this, the diameter of this fuel tank is bigger than a 747 is around, okay? So if you think about how big a 747 is, that's an airplane with 3 levels, right? You've got your cargo level and 2 passenger levels. And this is actually bigger in diameter than a 747. So we actually put it in this building, and we hook it up to these ginormous hydraulic actuators. And when I say ginormous, they're taller than I am, and I can't get even halfway wrapped around it if I were to go try to bear hug it. We're going to pressurize the tank, and we have these pneumatics, these actuators all the way around it, and we're going to start to shake it. And we shake it, and we shake it, and we shake it while it's pressurized at 46 PSI. That's a lot of PSI. You know, 4 PSI, if you take a 747 and you pressurize it at 4 PSI and you don't have the doors fully down, it'll actually sneeze and your cargo door will open up and slap the top of the airplane. Yeah, okay. I have some interesting stories. But 4 PSI is a really big deal. So having it at 46 is even bigger. And we'll actually shake it around just like it'll see the structural loads that we have when we launch it. And we do that every time because if we were to lose our fuel tanks, that's a pretty bad thing. That's a bad day for us. So we'll make sure that we don't do that. Let's see, I have a couple other ones in here. All right, now I was talking about qualification tests, and I told you we've got to qualify everything, right? So this is actually the parachute test for the Starliner. So what we did was we took a mock-up of the Starliner. It's a capsule that actually holds 5 people, goes back and forth to the space station. We actually took it up via a hot air balloon. That's how we got it up to things. And we actually tried to make sure our parachutes work. So you see the drogue is deployed. Now, this capsule isn't fully built at this point. It's a mock-up, it's a model. It had a full parachute system on it, but there's no avionics, there's no hydraulics, there's no life support system. It has mock-ups that mimic the weight and where the weight is going to be. And so we'll actually take it up and say, let's go see how well our parachutes work. How many people think that you can just drop a capsule? Right? These are tests that people don't even realize that we do. And again, we're going to do this at least once for every program. Now, we actually learned things from this parachute testing that actually caused us to go redesign our parachutes, even though we had a successful test. So you see the drogues come out, and pretty soon you'll see this will disconnect, and it'll leave, and then you'll see, there it goes. It's almost like I knew something was going to happen. And then you get our main parachutes out. Now, if you notice, if you've ever watched the Apollos land, you kind of see the same type of parachutes. They worked well for Apollo, so why reinvent the wheel? We actually used a very similar system to what they used for Apollo. And so we got good chutes. Now, what we learned through this testing was that up here, those guys were actually getting tangled and breaking early. And they weren't supposed to do that. Now, it still worked. We safely got our capsule down, but it did not meet the qualification. We did not pass our qualification test. So even though these parachutes showed that they were good, it showed that we could land safely with them, it still didn't pass the qualification because we have a lot of restrictions against us for qualification. So in order to land safely for one of these, our qualification shows that we have to be able to land with not 3 parachutes, but 2. So we have to show that we could completely lose one of those parachutes and still get our astronauts down safely. So with our 3, we had no problems. But when we were measuring the loads coming off of what we had here and what was coming up, we actually found that we had more loading than we anticipated on each of the parachutes. So if we actually lost one of them, that would then increase each of the loads on the remaining chutes to a level that we wouldn't be able to survive the landing. Those chutes wouldn't be able to take it. They would have actually separated from the vehicle. So we actually had to go and redesign those. Now, again, qualification testing is the fun testing, as I like to call it. Now, and even in qualification testing, we deal with some pretty hazardous stuff.
9.
So this is actually the pad abort for Starliner. So you see the Starliner here. And what we're going to do is we're going to launch it. The whole point is that we want to show that we can get astronauts safely back to Earth if we have to abort the launch. So we actually launched it without its rocket. So kind of fun. Who saw that orange spurt that came off of it? Yeah. Does anybody know what that is? Any thoughts? What do you think it is? You think it's fire and smoke? Good guess. Yep, that's, you see the parachutes coming, right? There's the parachutes, because we got to show that we can land, right? But, oh, there was that orange poof again. What do you think it is? Exhaust? Maybe. It actually isn't. What that orange is actually something that we call MMH because it's a big mouthful, but it's monomethyl hydrazine. What that is it's the rocket fuel. When they actually launched this, again, qualification is where we learn whether we've done our job right or not. In this case, we had problems, and so we had to go back to do a redesign. So that's the base heat shield coming off, and then you'll see that the landing airbags will come out. So part of what pad abort was to do was to, again, prove our, notice, how many parachutes do you see? How many did I told you we need to be able to show we can land it safely? 2, right? So that's part of that qualification. We also have our airbags. Starliner is the only man-rated capsule ever to be built that is actually going to be certified to land on the ground. We do not have to land in the ocean, which is a really cool thing. And let me tell you, the astronauts really appreciate the fact that they don't have to sit bobbing in the waves hoping somebody gets there in time, right? We land on the land, which is cool. It's a really good thing. But that puff of red that you had seen is actually monomethyl hydrazine. It's actually the fuel that we use for the vehicle. It's actually the fuel that we use once we get to space. So the idea is what's on the crew module and the service module, that fuel is actually used once you get to space because getting from Earth to space is done by the rocket that the vehicle sits on. So monomethyl hydrazine is really cool because you don't need a lot of it to get a lot of power. And when you're going to space, weight is everything because it takes a lot of power to get off of Earth. Now, in this case, we found we had things that we had to learn. What did we learn that was good? 1, we learned that we can land with 2 parachutes. Awesome. 2, we learned that our landing airbags did exactly as they were supposed to. Awesome. 3, we learned that we had a problem in our propulsion system that was a little too fragile for an abort like this. Not awesome. So it caused us to go back and do a redesign. And when we did the redesign, we actually had to go back and look at the testing and actually show why did this failure happen? What was the mode that caused it to fail? And how do we go back and fix it? And a lot of our times when we're doing these engineering and looking at all this stuff, that's a lot of what we're doing, is we're going back, we're trying something, we see what it does, we learn from it, and we do it again. And we do it again. And we do it again until it's actually doing exactly what we want it to do. Because the last thing we want to do is put our astronauts out into space, or even in the launch pad for that matter, without knowing exactly what we can expect from our vehicle. How many people think that space travel's safe? A couple people, yeah, so. Now, historically, space travel actually has a human life accident every 20 years. Every 20 years, generally somebody will perish in a space-related accident. So you had Apollo 8, where you had the fire on the vehicle. Now, that fire on the vehicle, does anybody know what that was from? It was an electrical fire, but the electrical fire itself wouldn't have been so bad had the entire capsule not been filled with oxygen. Right? And so we learned something even from those accidents. Now, we actually now have qualification tests that show that we have to be able to maintain an Earth-like atmosphere on our rockets and on our space capsules when human life's going to be aboard. And it's an Earth-like atmosphere. It's not an oxygen-rich atmosphere, and it's not oxygen-rich because of that fire. It's something we learned. And so now when we do our qualifications, those specifications that we have to go to have changed. So every time we have an accident, something changes. Challenger was almost 20 years after the Apollo 8 accident. Columbia was 20 years after Challenger. How long ago was it Columbia? Anybody remember what year Columbia had its? 2003. If historically we have a human life accident every 20 years, yeah. So that's why we test, right? There is nowhere to stop to go to a 7-Eleven when you have a flat tire to call for help. AAA is not coming. If you can't get there, you can't get there. And you may not get there alive. So we build in a lot of redundancies and we check a lot of redundancies. Starliner, for example, had our OFT mission. It was our very first mission. It was an orbited mission that we were doing. It was one of our certification missions. Generally, when you're doing human spacecraft, you have 2 missions that are required in order to do certification. 2 certifying flight test missions. One is an orbital flight test. How many of you guys saw on TV last year or so Artemis's launch? Yeah. Let me tell you, it was really cool watching that sucker go at 3:30 in the morning, and I was screaming the entire time. And my family laughed at me hysterically because I was there for most of the build of the core stage. It was like launching one of my babies and watching them grow up. And so I was going, go baby, go, go baby, go. 8.5 seconds, let's do it. 8.5 minutes, we got it. And I yelled at it the entire time it went. Just ask my kids, they're in the back. They were laughing hysterically at me the entire time. But when Starliner did its first orbital mission, it was supposed to go up, it was supposed to orbit, it was supposed to dock to the International Space Station. Guess what? It didn't make it to the space station. It didn't make it there. Now, if we had had astronauts, they would have been perfectly safe because we had enough redundancies that we had that built in. Now, what had happened with us is we found out that, oh, you know what? When we launched and we went to battery power, it actually reset one of the clocks on our flight software that we didn't realize it was going to reset. It was something that we missed during testing. But that's why we do those certification tests and why we do an orbital test without humans aboard before we put humans aboard. So because we didn't get to the space station the first time, we had to do a second orbital test. I think I have the launch of that one on here, do I? Let's see. No, core stage. Let's go back to the other page. Let's go back. Oh, nope, I have the Artemis launch, not the OFT-2 launch. But the Artemis launch is still really cool to watch.
The 4 core stage RS-25 engines gimbaling around.
Again, we're going to gimbal the engines.
To steer the rocket into space.
Now, this is a certification test, and this is the orbital certification.
109%
So it's the orbital flight test. They still have one more flight test that they have to complete before certification exists. Starliner still has one more certification test we have to complete before we exist. Our Starliner certification test with humans on board is scheduled for May the 1st. As a matter of fact, as I'm standing here with you guys today, my team of engineers is pushing hydrogen and rocket fuel onto the spacecraft.
The same milestone is coming
right now.
For the core stage.
Right now, that's what my team of engineers are doing, is putting rocket fuel onto the spacecraft in Florida. Yeah, it's really kind of cool. Now, what's cool is that I have teams of engineers. My engineers sit in the back room for all of these launches. You know when they who's watched Apollo 13, right? And you guys hear
The
when they go,
rocket's core stage, which
instrumentation!
houses the
And they
three
start
flight
yelling and trying to
computers,
figure out
is
what's
now
going on.
on
And they're
battery
talking to
power.
people not
So
in the
there is
control
no more
room, but
hold
in
time
the back
available
room to
because
try to
there's no
figure out how
more
to fix
margin on
things.
the batteries.
Those
So
engineers in the back
if
room
we
are my
have
engineers.
a hold, we'd
That's
have
what
to
my
recycle
engineers
back
do
to
on launch
T-minus
day and on
10
mission
minutes and
day.
recharge those batteries.
So you're going to see during the
The
launch,
count continues.
it happened in the middle of the night.
A note
Now,
now,
they actually
shortly after
attempted to launch
liftoff,
this rocket 4 times? 4 times? 4 or 5 times without
shortly after
success?
liftoff,
Because
Mission
there was
Control
issues on
Houston
the
will
ground
take control
side.
of the rocket, and my colleague, Leah
That described
Cheshire,
it
will
usually
take over
within
commentary. T-minus
20,
50
30
seconds
minutes of
and
when it was
counting.
supposed to go.
Coming up at T-minus 33 seconds, the
So
GLS
what's going to
will
happen
hand
is
off
that it's
control
going to
to the
convert
ALS.
over to
This is
battery
the
power.
autonomous launch
So while
sequencer.
we're on the
board
launch
the
pad,
rocket, it will take
it
over
actually
command
gets
and
power
control
from
of
the
rocket.
ground. So you
The
can see
ALS
what these
will check,
arms,
make sure there's no holes
these are actual
coming from the
umbilical
ground
arms that are
up
providing
until
power.
T-minus 2
So this is the
Go for
forward
ALS.
And
skirt.
we are go for ALS.
This is the inner tank.
The Space Launch
There's a
System
lot of,
is
between
now
those two,
counting
those are the
down to
navigational
liftoff of
systems for
Orion
the
on
core
its maiden
stage.
voyage to the moon.
This arm up here goes to the launch adapter and over
Launch
to the
team
service
will
module of
overcycle the count.
of the Orion capsule that sits on top of this.
Sound suppressor water now flowing
15.
under the ML.
Yeah, it's really
And here
cool.
we
Let me
go.
tell you, when you
Okay.
wait for this,
Hydrogen burn
and you're
off
standing
igniters
outside and you're
initiated.
watching this and
7,
waiting,
6, 5. Core stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise
it's really
together
cool. This
back to
happened
the
at
moon
3:30 in the
and
morning.
beyond.
And it lit up the sky like the sun was rising. Now we were standing about where you had that picture where you had the water in front. That's about as far away my family and I were from when this sucker launched off. Meanwhile, I'm screaming and screaming and screaming at this. Now, you notice that they started the main engines before the solid rocket boosters. Does anybody know why? My boys know why. You know, when you light a solid rocket booster, at that point you cannot turn it off. Once it's lit, it's gone. And it will burn until all of it is burnt out. If you look at the core stage rockets, the core stage engines, we can turn them on and off. And if we turn them off, we can always restart them. Because this guy that you now see in the sky was the same one you saw bolted to the ground for Green Run. The exact same one, the exact same core stage.
Quiet here in the loops in mission control. Full core stage engines throttling down ahead of passing through max Q.
You actually, so the time of day that you launch actually has to do with the orbital mechanics of where you're trying to go, right? So in this case, they're actually going to, for Artemis 1, they actually needed to go around the moon, right? And so it was looking at when do you have,
20 miles per hour.
one, you got to have good weather, right? That can describe you. But how can you get to the moon? You got to look at the orbital mechanics to make sure you can get there. Because if you're launching and the moon's going to be on the other side when you get to it, it doesn't help you, right? And so that's, so depending on where you need to put your payload will determine what time, day, or night that you actually launch.
In mission control Houston as
And so the first several times we attempted to launch this, it was like 8 o'clock in the morning.
We're now 16
Right? The first time we launched it was 8 o'clock, and then it moved back a little bit, then it moved back a little bit, then it moved back a little bit, to the point where we were at 3 o'clock in the morning. And it's all based on the orbital mechanics.
Standing
And
by
that
for
is math
solid
I
rocket
can't
booster
do.
jettison and shortly thereafter.
But when they actually go to do this, you guys see that? That's actually separation. So the solid rocket boosters
Confirmation
just
that the
separated.
solid rocket boosters have separated these 177-foot boosters.
And so they're going to go and
Now
they're
the
going to
core
come back
stage
to Earth.
continues to power the flight of Orion, all 4 RS-25 engines firing, traveling over 3,400 miles
So
per
you see
hour,
they're
46
still
miles
lit.
downrange.
They're finishing the rest of the fuel, but the rocket went on without them.
2 minutes and 36 seconds into the flight. Hearing nominal calls here in Mission Control Houston.
And nominal calls are a good thing.
We've still got 4 good
Nominal
engines
calls
on the
are a
core
really
stage.
good thing.
Next up, we'll be looking
But
for
we
the
watch
service
it,
module
you
fairing
see
to
this kind of
separate.
data. This is
three
actually the
15 by
data that we
15
actually
foot
look
fairing
at when
panels,
we're in the control
providing
room.
structural support,
And so
protecting
each
the service
position in the
module.
control
Those will
room, when they're
separate
doing
about
these
3
tests,
minutes and 11
actually have a
seconds
different
into
set of
flight,
data
and
they're
very
looking
shortly
at.
thereafter
They
will
have
be
groups
followed
that are,
by
like
the
this
launch
one
abort
looks
system
like this is our
separation.
navigational data. We also have a screen that'll have propulsion data, stuff that'll
Just
have
over 3
hydraulics
minutes
data,
into the flight of
stuff that'll
Artemis
have
1, now
temperature
traveling
data. I'm
over
looking at the
4,060 miles per
environmental
hour,
system
83
on it.
miles
For
downrange.
for flight tests, whether they're
We
crewed
just
or
had
uncrewed, we
confirmation
actually
that the
even have
service module
additional
fairing has
instrumentation on there
separated.
called developmental flight instrumentation, DFI. but it's a series of strain gauges and things, so we can make sure that it's actually
And that
seeing
the launch abort
the
system
loads that we
pyros have
expect it to
fired,
see.
separating
All of those
from
things that we
Orion
tried to
as well.
demonstrate during
For
qualification
future
tests
crew members,
by looking at the individual components. When you saw like the developmental test that I showed you, the qualification test where we actually blew up the liquid hydrogen tank, if you noticed it wasn't connected to anything else. Well, when we go and we do a test like
we
this,
just
there's
heard
actually
the call
stuff
for 3
bolted to
engine
the
press,
top and the
meaning
bottom
if
of that
SLS
hydrogen
were
tank,
to lose an
which is
engine
going
at
to
this point
change
in
how
the
it
mission, we could
behaves.
still achieve a nominal
And so
mission.
we actually
We
want to
would
watch
just have
to
an
see what
extended
happens.
main engine cutoff time. However, we still have 4 good engines, all at maximum thrust right now, powering the first flight of
Do you guys
Artemis
wanna watch
at
the rest of this?
5,200 miles per hour,
Yes? Okay.
148 miles downrange.
So we've lost our SRBs. Now, do you remember when it launched, it had something at the front? Notice it's not there anymore.
We're 4 minutes and 16
What was at
seconds
the front
into
there
the flight of
was
Artemis
actually
1.
the launch abort.
So
Remember when
far
I showed you guys
we've
the
had
pad
a clean
abort system on the
ascent.
Starliner
We saw
where
those
we
solid
launched
rocket
it off?
boosters jettison
That
about 2
actually
minutes
is
and 11
done
seconds after
by this little
liftoff,
tip here.
shortly after we had the service
tip that we
module
have on top?
panels
So if
fairing
something
separate,
happened during the launch
as
where
well as
the
launch
rocket was
abort
going out of
system. The launch
control or
abort
we
system
couldn't have
was
it
inert
anymore,
for this flight,
that launch abort
except
system
to
would actually
perform
light
this
and
separation.
separate the capsule from the rest of the rocket to get the astronaut safe. But
Those
once
4
we get
core
to the
stage
point
engines will
where
continue
it would be
to
too dangerous
fire
to do that,
and
we
power
actually
the flight
jettison
of
it.
Artemis 1,
And it doesn't
now
stay with us
traveling
any
over
longer.
6,800 miles per hour, 229 miles
Did we
downrange.
freeze or is it still going? Oh, it's still going.
Booster flight controller reports
There
that
it
the
goes.
engines are looking good.
And so you can still see those main engines. And it starts looking like a star. Gets really teeny tiny.
Our core stage main engine
You
cutoff
can
time
still
is about
hear
8
it though,
minutes
which
and
is
3
kind of the
seconds.
really weird
we
thing.
are now
But by the
5
time you're
minutes
seeing
and
it, it looks
11
like a star like that,
seconds
it's
into the
over
flight,
Africa.
7,656 miles per hour.
Think about that. You can still see the rocket when it's over Africa.
Again, 4 good core stage engines, those 4 RS-25 engines. The last time those core stage engines flew, they were taking space shuttles to orbit, and now with upgraded capabilities, they're launching the
Yeah,
future of
that's the
human
interesting thing.
spaceflight.
So the way they designed the core stage for Artemis is actually reusing a lot of the shuttle parts. So it
5
reuses a lot of
minutes,
the shuttle
42
engines and the
seconds
shuttle
into the
things.
mission, we are now traveling 8,800 miles
again,
per
you
hour,
see that little star?
345 miles
That's our rocket.
downrange from the launch pad at
That
Kennedy
rocket,
Space
when it's
Center.
laid on its side, is longer than a football field. Yeah, big,
Again,
huh?
we are anticipating core stage main engine
You can go
cutoff
up
at
to
about
it
8 minutes
when
and 3 seconds.
this is on its line.
And about 10 seconds later, we'll see core stage separation, at which point Orion and the interim cryogenic
Do I have a
propulsion stage will be
picture on my
flying
computer?
free.
I don't know if I do or not. Don't think I do. All right,
Now
I'm going to
traveling
escape out of
over
this because it's
10,000
going to get
miles
into
per
kind of
hour,
more of the
6
same
minutes and
thing.
15 seconds into the flight of Artemis 1, 427 miles.
So that's what happens during qualification testing into some of our certification testing. And so, but we're looking at all of this stuff. Do you guys see this part? Life control systems? Yeah. So we actually have to keep our astronauts alive. So, right, who would have thought? We got to keep our astronauts alive. You know. So, and I have to tell you, astronauts are really picky, especially when it comes to the temperature of their cabin. That is actually the biggest complaint we get from our astronauts is, I don't have good temperature control. It's like trying to control the temperature in a car. Like, do you ever get it exactly where you want it? No, not really. I mean, it's still going to be comfortable. You're not going to die. But they'll tell me, like, it's really interesting because, like, one day it'll, like, and I've got thermocouples in there, right? Because we're testing this still. So we'll actually have our thermocouples all in there, so I know exactly what the temperature of that environment is that they're in. And they'll be in one day and they're going to tell me, oh, you know, we were in there all day and it was so hot. Can we do anything to cool it off? I'm like, it was 68 degrees, guys. Oh, but it'll be so much better if we cool it off. Okay, we'll cool it off a little bit. So we cool it off just a little bit. Or at least we tell them we're going to cool it off just a little bit. And then they come in the next day and they're like, gosh, it was so cold in there today. Guys, it was still 68 degrees. So it actually gets kind of difficult sometimes trying to make it work. Now, remember I was telling to you guys about the oxygen in the atmosphere of the vehicle. We got to keep it Earth-like, right? Again, we can't have it too oxygen rich because then we have fire hazards. We can't have it oxygen depleted because then they can't breathe. And you know, astronauts want to breathe. It's one of those things. But one thing that I thought was really interesting is humidity. We have a humidity requirement on what the capsule has to be. Now, humans can survive in really low humidity, right? I mean, if you go out to the desert, the humidity is what, maybe 1-2% sometimes on the driest days? I mean, you feel it, it's not real comfortable, but you can feel it, it's not going to kill you. If it's 100% humidity, does anybody know what 100% humidity feels like in Atlanta? Yeah. Any of us who lived anywhere in the South knows exactly what 100% humidity feels like. The humidity range that I'm allowed to have on this vehicle is between 40% and 60% humidity all the time. All the time. Now, you would think that humidity would stay the same, right? If I put them in and we go in there and there's nobody creating, like we don't have any weather conditions really that are going inside the vehicle, why would my humidity change? Breathing, sweating, humans going to the bathroom, drinking water, different things along those lines will actually raise our humidity level, so we actually have to put dehumidifiers in. And part of why we have such strict humidity levels actually isn't even for the humans. It's for the electronics. Because if it gets too dry, you'll start getting electric shocks. If you've ever been to the desert and you've been walking on carpet, how often will you shock the people that you touch? And you get the, duh! Yeah, well, electronics are extremely sensitive. And so if you were to do that kind of electric shock to a piece of electrical equipment, you could potentially damage it. If you damage electrical equipment and now maybe your avionics don't work and you don't have good navigation, can you stop and ask for directions in space? No. So that's a really bad thing. Now, if you have too much humidity, the electronics will actually start to corrode. They corrode, they start rusting. Yeah. Now, water's a really great conductor. And so you can short things out, you can do all kinds of different things when you get too much humidity and you start getting the corrosion, is that you're actually going to start making electronic connections that you don't intend to. And so you can corrode it. Electromagnetic interference. That's kind of a weird one, don't you think? I mean, all of us have electronics in our phones all the time, right? We carry electronics with us everywhere. But all of our electronics actually give off electromagnetic interference. All of the electronics on the planet do. Even these lights up here will give off electromagnetic interference. Now, that isn't necessarily as big of a deal on Earth because, again, we're not going to fall out of the sky, right? It's not going to kill us if we have bad EMI. We just may have signal loss. Our TV is going to go fuzzy and we're not going to be able to watch, the next episode of Survivor maybe, right? But it's not going to kill us, right? Again, when we get out into outer space, we have to be able to deal with the electromagnetic environment. And there are some added electromagnetic environments that they have to deal with in space. Yes, ma'am? That's exactly it. Just like the key card against your phone type deal. That's exactly it. Now, how many of you guys have actually heard about, people being concerned about solar flares and our electronics on the Earth acting up? Now, we have the benefit that our atmosphere protects us from that. In space, they're even more susceptible. And that's all electromagnetic interference. And we still have to make sure that all of our equipment can handle that. So when we do this qualification testing, we're looking at all of this stuff and even more. Every last thing that you could possibly think needs to be tested, we have to test when we're doing qualification testing. We have to think of every contingency that could ever possibly happen and say, how is it going to happen and how do I make sure it doesn't happen? And again, we aren't always right. We don't always know everything. There are some failure mechanisms that we haven't even thought of. And that's what leads to some of the accidents. That's what led to Challenger when it went and having too cold of a O-ring and putting it in a position where that got too brittle. So we didn't know that we needed to test for it then. Do you think we test for it now? Absolutely. Apollo 8 with the oxygen levels, again, it changes our requirements that we have to change to. Every time we have an accident, we learn something and our requirements change. How we talk to each other changes. And so it's really important. But again, the cool thing about the qualification testing is it's the opportunity to demonstrate to failure. If you're going to fail a system, you want to do it during qualification testing because that's the point where it's the safest to do. Now, that's not to say it's completely safe because obviously we are blowing up hydrogen tanks, and if anybody realizes how much explosive TNT that is, that's a significant amount. And that's a really dangerous test, but because we know it's dangerous, because we know what's going to happen, because we know the force, we can put in precautions to make it safer for people. So we clear out around it. Remember when we were talking Green Run and I said nobody was within a mile of that vehicle? And it was specifically because just in case something happens, we don't expect it to, but if it does, how do we make sure that people come out alive? And that's part of what we test for. That's part of what we do. So we're done with our qualification testing. We go into certification testing. Now, the certification testing for human spaceflight has 2 flight tests, exactly 2 flight tests, normally, assuming that you meet the objectives of both. Now, the first flight test will always be an unmanned flight test. This is where you're showing that the vehicles can go out into space and they can safely return to Earth and actually perform everything that it needs to do. Like I said, with Starliner, we actually had to do 2 because we didn't make it to the International Space Station the first time, so we couldn't demonstrate that our docking system worked. So we had to go up a second time. Our second time, we got to the International Space Station, we docked, everything was great, we landed safely, everything was perfect. OFT2, check, our orbital flight test is done. You saw the launch for the orbital flight test of Artemis. Now on that one, they actually took it up and actually went to the moon and back, and actually orbited the moon and went further than any manned capsule has ever gone to date. Now, for OFT, we finished OFT2 for Starliner. We now have our certified flight test coming up. This is when we put human beings on it for the first time. Now, these astronauts that we put on board are with us very early on. They're highly trained and will be more trained on this vehicle than any other astronaut that will ever fly this vehicle. They know it from in and out. They are in the factory with us building it a lot of the times and seeing how it works as we build it, as we do tests. They're with us every step of the way so that because let me tell you guys, if I'm strapping myself to a rocket that's going to go up to space, I certainly want to know the people who built it, and I want to know that it's safe, because this is not a child's game. And so these guys are in with us in the factory. They watch us as we test. When we did those qualification tests, oftentimes they come so they can see it and they can raise concerns and they can go, you know, I'm not too comfortable with this. This worries me, this scares me. And sometimes they have really great inputs. Other times they just think things are too hot and too cold and they're exactly the same temperature that they were the last time. But that's okay. Our job is to make sure they're safe. So, all of our certification tests is actually done on the actual flight vehicles. So once we get done with our unmanned flight test, our orbital flight test, we'll go to a manned flight test. Like I said, we'll have the astronauts actually on it. Now, usually your manned flight tests, your first ones, are generally shorter than they will be long term, right? So for my crewed flight test this time around, our mission is only slated for about 2 weeks, but we can stay on the ISS for up to 6 months. And we're cleared to stay up to the ISS for 6 months. But we have a lot of paperwork to do after certification to file with NASA and the Space Force and our international partners. Because when you go to the space station, what's the first letter of International Space Station is I for international. We have 14 different countries that participate, and everybody has to sign off to tell us that we're okay to come to their station. Yeah. So we're getting ready to do ours. So in our case, we have 2 astronauts that'll go, and they'll fly up in May. May 1st is actually our crewed flight test. That's at least what we're scheduled for. Weather could change it because launches are always dependent on weather, space weather included. But we'll get to go take people up. Now, when Artemis 1, when they go to do it, they will actually have a crew of 4 individuals. It'll be the first time a female has ever gone anywhere close to the moon. It'll be the first time a person of color ever goes out to the moon. And they're going to do an orbital test around the moon. They're actually not going to land at the moon this time, but they're actually going to follow the same flight trajectory that our orbital test did. Now, remember when I told you guys that orbital test went, a manned capable capsule went further away from Earth than has ever been done before? Those 4 astronauts will be the first 4 living people ever to be that far away from Earth, ever in the history of the world. It's pretty cool. We're actually starting to get to the point where we're exploring more. We're getting further and further out. And the whole point of Artemis is actually to build a space station around the moon so we can practice actually how do we land on the moon? How do we mine on the moon? How do we get water? How do we grow plants? so that as we get further and further away from Earth, where we can no longer resupply quickly, the astronauts and things can inhabit and be livable. It's actually a really cool thing. So, we're going to do it on the actual flight vehicle, and it starts during the build of the subsystems. So we actually do things that we call acceptance tests that are part of it. And so it's a build a little, test a little type environment. So when we finish out a subsystem of the spacecraft, whether it be a fluid system like your propulsion system, your landing system, your oxygen system, your avionics system, we have to go back and test all of it to make sure it works together as a system. Because the qualification test. Yes, ma'am.
Just for 1 second, if anybody has a desire to see the 8 o'clock planetarium show, we've got about 4 minutes to make it across the...
And I won't be offended if you guys leave because it's a really cool show.
Just wanted to say that in case anybody wants to see.
Yeah, if you guys want to go to the planetarium show, I'm not going to be offended if you go. Oh, don't worry about it, kiddo. So we're going to make sure all the subsystems work with one another during the integrated testing, right? And then the other really key thing about certification testing is this one down here, non-destructive. Unlike our qualification testing, I can't intentionally break it. I can't intentionally blow it up.
I know this is certification testing, but is there some place where we would be able to observe, like, it doing its thing, so that way, or is it something that's recorded that we would be able to see as, like, if we'd like to see it later?
So there are some places you can go do it. So one of the best places, and like all of the videos that I'm showing you actually come from YouTube of all places, right? So if you go to YouTube, especially, there's actually a NASA channel on YouTube that actually shows a lot of this testing and a lot of these details. Sometimes you'll even get to see on those YouTube channels the live feeds from the ISS where they're actually doing experimentation on the ISS real time. And it's really, really cool. But anytime you have these big launches and things, those are almost always available on YouTube. So SpaceX will do theirs, we'll do ours for Boeing. United Launch Alliance will show theirs as well. The Delta IV Heavy, the very last Delta IV Heavy ever to launch, will actually launch out of Kennedy Space Center next week. And so that's kind of cool. It's the end of an era for that rocket. ULA will launch Vulcan here in another couple of months. And that's actually a brand new rocket, so they just did their orbital flight test. And so it's, right now, Vulcan is slated to stay an unmanned capacity, but we're actually looking at it to potentially make it a manned rocket. But anytime that there's a launch at the Kennedy Space Center, if you go to Spaceflight now, it'll actually list every launch anywhere in the world. And you'll be amazed at the places that it launches out of. Like, because the Russians will launch out of Kazakhstan. You'll have the Indians that'll launch out of the area in India. You got stuff at the Marshall Islands. We launch rockets at the U.S., both at here, I'm not at Kennedy Space Center right now, but where I live at Kennedy Space Center, we'll launch rockets out of there. There's Wallops Island in Virginia where they'll actually do launches, and they actually do some space launches out of Vandenberg Air Force Base in California as well. So launches happen all over the world, and there's several launches every day, or every month, I should say. So at Kennedy Space Center right now, we actually last year sent a record of 70 rocket launches out of Kennedy Space Center last year. This year, we're actually slated to have 96. So if you want to come see a rocket, go to Spaceflight now and you'll see when things are scheduled. So that's at least the one that I like to use. So, and then finally, the acceptance testing. Now, the acceptance testing happens all the time, right? And it's just a subset of the certification, except for the fact that it happens on every single build of the vehicle. Because when we do the acceptance testing, we're actually making sure that the vehicle is built properly. So we're making sure there's no shorts in the wire. Did we cross pins on some of the connectors? Did we have any leaks in our propulsion system? Does our avionics and flight software talk well together? We're going to look for those for every single build. But that's what happens with testing. Questions? That one.
I've got a question. I'm going to come over with my microphone so that we're recording this. You can see this talk.
And I have a bonus slide if you guys can figure out what a good question is for it. Bob here knows what my bonus slide is. He's trying to get the microphone to work. I can reiterate the question if you want to start that way.
Buddy in the booth there. There you go.
I was curious about the boosters and everything that drops off of the vehicle after it takes off. What happens to all that stuff? And does it ever go wrong and maybe land on somebody's house or or something like that?
Well, so it depends on which rocket you're talking about. So SpaceX, for example, their rockets, their boosters are not solid rocket boosters. They have a different type that actually uses kerosene. And so SpaceX will actually land on their landing platform and reuse them. And they have several that have been reused multiple times already. Solid rocket boosters, you can't really reuse them, so they go off to the ocean and become fish food. That's generally what ends up happening with the parts that come off. Core stage, same thing will happen is it'll go to the ocean and become fish food, but a lot of it'll burn up as it comes back down. Do things go wrong? Yes. But there's a reason why we launch generally in areas that are fairly unpopulated. You know, I say Kennedy Space Center, you know, and everybody's like, oh, well, it's close to Orlando and Cocoa Beach and things. But Kennedy Space Center is really, really large, and the area around the launch pads, we probably have a good 10, 15 miles before you get to real civilization. And we do that specifically because things can go wrong. As a matter of fact, there was a Delta II rocket that actually blew up while it was launching. It was only about 200 feet off the ground when it actually blew up. And this is before they changed the rules about where the Launch Command Center was. And so at the time, the Launch Command Center was actually only about 200 yards away from the launch pad. And when it blew up, all of the debris came down. And all of those individuals had their cars catch fire because it was essentially blown up by rocket debris. Not only that, the building they were in caught fire, and it was too unsafe for them to actually leave the building, so they had to stay in the building that was on fire, because if they left the building that was on fire, they were going to be in an environment where debris of fire was coming down on top of them. So they actually ended up having to go to a back room, don smoke hoods, the whole 9 yards. It was an unmanned rocket at the time. Nobody was actually seriously hurt or injured. But hearing the stories from the people who tell it and who are actually there is incredible. But could you imagine calling your insurance going, so I need to file a claim because my car was blown up by a rocket? I was like, what? So those guys that day, they actually had to send a bus to come pick them all up and had to have their family members meet them at the Kennedy Visitor Center because they had no way to get home.
Another question. Oh,
We got one
see-
down here and one there.
What?
We'll go up there. He's got.
Come up.
We'll come back down.
Come up this way.
Okay, what was the best launch or most successful launch in spacecraft history?
Ooh. I don't know. And the reason that I say I don't know is because there are so many different launches and so many different vehicles that each one adds to the wealth of knowledge and our capability to go to space. You know, some of the best launches and most successful were ones that weren't even really technically successful. So when we were actually learning the most was during the Redstone era. And during the Redstone era, we blew up a lot of rockets. But we didn't know yet what we needed to test for in the different failure modes. But because we were blowing them up as quickly as we were, we actually learned a lot faster. So I would say maybe that one. But again, every iteration, every generation, and every platform adds something to the wealth of knowledge. It's like asking me what's the best car ever built, right? You look at them, they all bring something different to the table, and they have different tasks and different jobs. But we can't do any of what we do without all of them.
Question right here.
Yes, ma'am. With the video that you showed of the hot fire testing, do they still conduct any of that testing in Huntsville?
No, they can. Generally, a lot of that testing no longer is done at Huntsville, at Marshall, because Huntsville's gotten a little too crowded, and people started complaining about the noise. So the hot fire testing and a lot of the hot fires that we do now are actually done at Stennis Space Center in Mississippi.
Down
We
this
had one
way?
here.
Oh, yes, okay. All right, we're going to make this the last question since we're running a little over. So
And I'll stay later if you guys want to ask more questions. So don't feel like you have to ask now and it won't be done.
All right, come right down this way.
So from start, when you design the rocket, all the way through the testing to launch, approximately how long does that take? Or is it different for each type of rocket?
It's different for each type of rocket, and it depends on how complex in the mission of the rocket. So Artemis, for example, so we're still not done certifying that one, right? And so we're actually not going to have our crewed flight test mission until sometime next year. But they actually started designing and building it in 2006, right? So from 2006 to 2025, almost 20 years in development in getting it to certification. But it's a really complex system, right? And multiple companies are involved. So where Boeing actually builds the core stage, there's a different company that Lockheed Martin builds Orion, which is our capsule. You know, we have a Delta IV type, we have a Delta launch vehicle second stage. We have a different company that does our SRBs, right? That's orbital. You know, so it really kind of varies depending on how complex it is. The other thing is, like, if you look at, say, the SpaceX Dragon, right? So they actually got to a crewed version of it pretty quickly. But the reason they got to a crewed version pretty quickly is because they had been certified to fly uncrewed to and from the space station for 10, 15 years before anybody ever thought to say, hey, why don't we make this a crewed vehicle? So when you already have something that's mostly certified, it's easy then to just convert. So it really depends on what the mission is and how much of the development's already been done and you're building off of something else.
Well, let's give a big hand for our speaker tonight.
And for the question that wasn't asked, why space? This is all a bunch of stuff that was developed because we went to space. So people always think that we go to space because we're pompous, we just want to see what's out there. But space actually really does provide us benefits here. My grandfather was saved for 30 years by a pacemaker that was developed because of our space exploration and being able to do those artificial defibrillators and things. So for 30 years, the space race kept my grandfather alive. All of us use cell phones with GPS all the time. That's part of our daily lives. All of that's from space. So going to space actually makes our lives better and keeps people here alive a lot longer. So.
Thank you. Thanks, everybody, for being here.
That was great.